yours.
Thank you for the introduction and for the invitation also. Thanks a lot. So yes, as you said, this is a joint work together with several collaborators, as you can see here. So what we did is that basically we tried to put together theoretical and numerical results to better understand the electrohydrodynamic interactions of drop pairs. So we started by looking at clean drops, and more recently with PETIA, we extended this work for surfactant-covered drops also. So there is also another person that is not mentioned here, but I want to mention, which is Anna-Karin Thunberg. So she didn't join this specific project, but she guided me through the whole process of developing the numerical code that I will present. So I need to thank her as well. Oh, I cannot, okay. Okay, so we are considering these tiny drops that change and deform in times, and so the geometry is not fixed. And for this kind of microfluidic simulations, the Reynolds number is very small, so we model the evolution of the drops using the Stokes equations. And on the surfaces of the drops, we have this insoluble surfactant, literally surface active agent. So these are compounds that can control and change the surface tension. So they are, sometimes they are naturally present on the drops, but they are also widely used in several pharmaceutical or other kind of application like food industries and so on. The word insoluble refers to the fact that we are assuming that this quantity lives only on the surfaces of the drop, so that it cannot spread in the bulk. And since it lives only on the surfaces, it follows the evolution of the surfactant follows a surface PD, which is a convective diffusion equation. And then in application like biomedical, pharmaceutical, engineering applications, sometimes we need to separate or detect, or so let's say that we have a mixed emulsion where we need to isolate a specific material, and then often an electric field is applied because different kind of particles will react in a different way to the same electric field. So what we want to do is to study how these drops will behave. And to model the electric field, we will use the liquid electric model that I will introduce now. But first, let's look at the outlook of the talk. So I will start introducing the problem formulation. I will talk about the numerical tools that I had to develop in order to deal with these kind of simulations. I will briefly talk about the asymptotic analysis, and then I will go to the validation and some new results. And then I will also say a few words about my future. So let's start by the formulation. So we have a system for the drop, the surfactant, and the electric field. So the XDT equal U, where X is the surfaces of the drops, and U is the velocity. And as I said, we have the convection diffusion equation for capital gamma, where capital gamma is the surfactant concentration. So we can see the first term is the convective term, then we have the diffusive term that depends on P, which is the Peclet number. And then the last term, K gamma U dot 10, this is a stretching term. So it takes into account the fact that the drops can also stretch. So the surface area is not fixed, as for example, it is for vesicles. And then of course, the total amount of surfactant should be conserved because as I said, it is insoluble. So we should take into account also the stretching term. And then we have the electric field that, as I said, we model using the liquid electric model. So basically this means that we assume that the charges are present only at the interface. So there are no free charges in the bulk. But there is also another assumption that we do for the electric field. So it is the here in the blue box, it is saying that the jump on the surfaces of sigma tilde En, where sigma tilde is the conductivity inside and outside the drops, and the En is the normal component of the electric field, this is 0. So this equation comes from neglecting unsteady terms in the conservation equation for the charge density. So this is quite a strong simplification. So we are trying to release this condition now, but for all the simulations that I will show you today, we also have this, this assumption. And then we have also the boundary conditions at the interface that prescribes that the stress tensor should balance the interfacial force, where the stress tensor has two components, a hydrodynamic component and an electric component. And the interfacial force again has two terms, sigma kn, where sigma is the surface tension, and then we have the second term, the surface gradient of sigma, that this is called the Marangoni term. And this is 0 if we do not have surfactant, while instead, if we have surfactant, the surfactant is related to the drop evolution through an equation of state that prescribes how sigma should change accordingly to gamma. So here I wrote a linear equation of states, but of course there are several others that you can use. So to solve for the Stokes equation and for the electric field, I'm using a boundary integral formulation. I will present the formulation only for Stokes, but because I don't want to bother you too much with equations, but the idea is the same for the electric field. So here we have the representation formula for the velocity u that depends on alpha, which is a parameter that takes into account the viscosity contrast. U infinity is a far field velocity, n is the total number of particles that we are considering, and S and D are the single and the double layer operator. So why are we using a boundary integral formulation? First of all, because we were looking for a highly accurate method. And using a boundary integral formulation, the jump condition that appear in the equation is naturally embedded in the formulation. So using other classical methods, the accuracy is limited by this jump. Also because remember that the geometry is changing, so that's a tricky part. But with a boundary integral formulation, we do not have this problem. Moreover, using a boundary integral formulation allows for a reduction of the complexity. Indeed, if you look at this equation, you can see that the integrals are defined only on the surfaces of the drops. So our drops are three-dimensional, so they live in a volume, but we don't have to solve the equation in the whole volume. We solve them only on the surfaces of the drop. So we move from R3 to R2, so that's a big gain. Another advantage is that if we want to simulate a large number of particles, we need to couple our method with some fast method like FMM or equal summation. And then those fast methods couple very well with boundary integral formulation. Of course, there are some drawbacks, like we have to deal with integrals, which may be tricky, but I will talk about it in a while. So let's go to the numerical method. So as I said, the integrals are defined only on the surfaces of the drops. So we want to have the best representation possible. And since the drops for the application that we are interested in have a spherical topology, it was super natural to consider a spherical harmonic representation, both for the drop surface, for the electric field, and for the surfactant concentration. So if we denote by P, the order of the spherical harmonics, then we found out that using even a very low P, we were able to represent all these variables with very high accuracy. And there are also other nice properties like orthogonality, symmetry, eigenfunction properties of the spherical harmonics that we will use and you will see through the talk. So in this method, I'm using a Galerkin formulation that basically means just that instead of solving for the physical variables, I'm solving for the spherical harmonics coefficients. And here is again, I'm gaining in complexity again, because thanks to the symmetric properties of the spherical harmonics, I don't have to solve the whole system, but basically I solve for half of the system. Not really half, but almost. So another gain. Okay, so I'm dealing with spherical harmonics. It doesn't mean that I can simulate only slightly deformed spheres, of course. We also tried the example with strong electric fields where the drops are strongly deformed, and we always find a good agreement. But I'll go back to simulations later. So as I said, we are using a boundary integral method. It has a lot of advantages, but we have to deal with integrals. So here I wrote only the single layer operator, but the idea is the same for the double layer. And this is the problem. So when we are computing the self-self interaction of a particle, at some point, x will be equal to y. So our denominator, x minus y, is 0. So the integral is not analytically well defined. And this is a problem, of course. We have to deal with this singular quadrature. Another similar problem is when we are considering multiple particles, and when the particles are getting closer, in the limit, x is approaching y. So x minus y is not 0. So the integral is analytically well defined, but we know that numerically it is very hard to compute it. And you can see that from my second plot, where I'm plotting the logarithmic error on the surfaces of the drops. And you can see that when the drops are getting very close, the error explodes. So I will not talk about the singular problem today, because here I wrote some bibliography, so I didn't take care of this particular problem. I just used results that were available. But the idea is that we can build an analytical solution based on the fact that the spherical harmonics are eigenfunction of Laplace. And then based on this, we can construct some modified weights for the quadrature. But this whole theorem holds only in the North Pole. So, and of course, our target point can be anywhere. So what we do is that wherever our target point is, we rotate the whole system of coordinates in such a way that our target point becomes the North Pole. And then we apply the theorem with the modified weight. So this is a pretty heavy, computationally heavy procedure, but it's super accurate because everything is analytical. Since we are dealing with spherical harmonic, the rotation is analytical and the solution is analytical also. So, that's great. It works very well. But I will talk about the nearly singular quadrature instead. So, well, since this is not an analytical problem, as I said, one may say, okay, this is a purely numerical problem. So why don't you just push the number of points so that the error will go down? So this is true and not. So if you look at this plot, I'm plotting the L infinity error of the single, this is for the double layer identity, I guess. But anyway, you can see the error versus the rescaled distance, rescaled with h, where h is the grid size. So you can see that if we increase the number of points, yes, the error is going down, but only up to some distance. So if the drops are very, very close, there is no upsampling that will work well enough. So we need to do something else. And this something else is this. So I took an idea originally proposed by Ying, Barrios, and Zorin. So we divided our volume in different regions. We have a well-separated region where the regular quadrature works well. Regular quadrature in my case means Gauss-Legendre in one direction and trapezoidal rule in the other. There is an intermediate region where upsampling, so increasing the number of points, is enough. And then we have the nearest region where we need to do something else. And this something else is based on interpolation. So this is a sketch of how it works. So let's say that here the pink star is my target point where I want to compute the integral. But I cannot compute it because by regular quadrature, the error is big. If I do upsampling, the error is still big. So what I do is that I first project this point on my surface, on the closest surface, and this is the red dot. And then I place a number of points, the green points, far away from the surfaces, where I'm able to compute the integral either by regular quadrature or by using the upsampling. And once I have the integral in all these points, I can do a simple 1D Lagrange interpolation to compute the integral in my target point. So the idea is super simple. It's just 1D interpolation, but this has been the longest part to implement because there are so many details, and also like, well, the first thing was, okay, I cannot check point by point distance. I have several particles with a lot of points. So I had to build some hierarchical code to check where I needed what. And then also in general, the projection of the target point on the surface is not a grid point. So in general, I don't have the value of the integral in there. So what I'm doing is that, again, I'm using a spherical harmonic expansion to interpolate somehow the value on the surface. And then there are other open questions like, okay, but how many points should I use for the interpolation, and how should I distribute them? Like, should I scale linearly or otherwise how? And also like all these three regions, how should I decide when I switch from one region to the other, and how much should I upsample, and all these questions. So I try to answer to all these questions in the paper that is cited here. And basically what I found is that if I push all these parameters enough, I can get really good accuracy. But of course, this has a cost. So what I'm trying to do now is, so if we would have an error estimate for this method, I could somehow make this method adaptive I mean that we could set the tolerance and then all these parameters would automatically be set. But it's not easy to get an error estimate for this 3D problem. Okay, I will go back to this point later. Another issue of dealing with drops is that, as I said, the drops deform. And this means that the grid point distribution may be distorted. So here I'm showing what's the problem. So there are two spheres, they are exactly the same surfaces, but I distribute the points in a different way. So in the first case, you can see that the spectrum decay with only one mode, while instead in the second case, where the grid is distorted, the spectrum decay much slower. And of course, we don't like a spectrum that decays that slow, because that may introduce numerical instabilities. So we would like some kind of procedure that, given the bad representation, bad in terms of spherical harmonic spectrum, will reparameterize the points in such a way to obtain the spectrum that decay as fast as possible. So this is an optimization problem. And Vera Paneni studied this problem already in 2011 for vesicles. And he got a solution based on Lagrange multipliers. So, and basically the idea is that we can minimize this energy that try to penalize the highest frequency mode, because this is what we want to do. And these A and M are coefficients, are like, some coefficient that penalize those high frequencies. And he was using this perfect high pass filter. So basically he's saying, so we don't know, where should we cut? Like he wants to fix some n cutoff, where after, like for all n bigger than this, we want to penalize. And he was using this perfect high pass filter that basically means that, let's say that P is the order of the spherical harmonics, he cuts everything that is bigger than P over 2. So I will call this reparameterization a physical reparameterization. You will understand why now. But we are dealing with drops. And so we do not have any local surface inextensibility as there is for vesicles. So our drops can deform quite a lot. And we have seen that using a fixed cutoff is not always working well. So the first thing that we did is that we made an adaptive cutoff that depends on the geometry. And why? The reason is super easy. So if we go back to the spheres here, you can see that if we have a sphere, we only need one mode to represent the sphere. And this means that everything that is bigger than mode 1 is basically noise. So we want to cut everything that is bigger than 1. But if we use a fixed cutoff, like let's say that P is 30, then P over 2 is 15. But anyway, like fixing the end cutoff independently from the geometry doesn't make any sense, because maybe we are cutting where we shouldn't. So again, I don't want to give you any details, but we were able to build this adaptive cutoff that basically look at the geometry and then cuts where it's needed to be cut. And it works very well. So this is an example. So we compare with an experimental results where there was a single drop in a shear flow. So what happens is that the drop initially deforms and then it reaches some steady state, but the tangential velocity is active because there is the shear flow. So the drop is not changing, but the tangential velocity is non-zero. And these are the cases where the reparameterization is fundamental. So here you can see that if we use this adaptive cutoff, then the energy is very stable, it's constant in time. But otherwise, the simulation is super unstable. So the energy actually explodes. But this is only one of the problems, because we would also like to have volume conservation. And moreover, the most important thing is that we have surfactant on the drop. So as I said at the beginning, the surfactant is a quantity that lives on the surfaces. So it is somehow attached to the grid points. So if we are somehow moving the points on the surfaces, how do we know the value in the new points? So here is a 2D sketch. Of course, we are working in 3D, but it was too complicated to show in 3D. So let's say that x0 is the initial configuration of the grid point distribution, and gamma 0 is the corresponding surfactant distribution. Let's say that using this Lagrange multiplier, we can compute this pseudo-optimal velocity that I call W. So I move my points tangentially to the surface to reparameterize and to get the optimal X star. So this is what I called before the physical reparameterization. So I know where the optimal grid points should be, but in this X star, I don't know the value of gamma of my surfactant. And of course, I cannot move gamma with the same pseudo velocity because this would be unphysical. So here is clear why. So the first and the second row are exactly the same, just with and without grid, so you can better see what's going on. So before the reparameterization, you can see I have a distorted grid, and then the colors denote the surfactant distribution. So let's say that I apply, I use this optimal velocity to move, to reparameterize the points. I get the optimal distribution of points. But if I move the surfactant with the same pseudo velocity, I am actually moving the surfactant, but it shouldn't change. I am just reparameterizing the shape, as I said. So the surfactants should look the same as the beginning. It shouldn't change at all. So what we did instead, we basically try to project these on the surfaces. Well, this is the geometrical explanation, but practically what we did is that we built a system for the angular variables, theta and phi. So instead of solving for the position, we solve for the angular variables. And that here I call theta star and phi star. And this is exactly what we were looking for, because we are using a global representation in terms of spherical harmonics. So if you give me the angular variables, I can give you the value of everything, of x, gamma, or whatever. And that works very well. And moreover, as you can see from this first plot, it has spectral accuracy. So here I'm plotting the error of the volume and of the area. So in blue is this with spectral reparameterization, and in red is for the physical one. So you can see that in this case, yeah, we do have spectral accuracy. And moreover, thanks to this, the surface constraint is naturally embedded in the formulation, because if we go back to the formulation here, this condition, so we have this constraint that was saying that we want to move the points tangentially to the surfaces. But since we are using now the spherical harmonic representation, this is naturally embedded in the formulation. And moreover, if we look at this picture, you can see that, yes, we are moving the points tangentially to the surfaces. But if delta tau is too big, we may end up too far. While instead, if we always project and we use the spherical harmonic representation, we are completely sure that we are on the surface and we do not have any delta tau restriction, as you can see from this plot. You see, with the physical one, the error is growing if delta tau is growing. And with the new one, it doesn't depend on delta tau anymore. Okay, so now a few words on the time discretization. So together with Sarah Paulson at KTH, so she was working on drops, but in 2D. So we studied a combination of midpoint for Stokes and an implicit-explicit Runge-Kutta for the convection diffusion equation, so for gamma. Why? Well, because as I said, gamma has a convective term and a diffusive term, and they need different treatment. So of course, the convective term wants to be treated explicitly and the diffusive term implicitly. And we were able to make this code adaptive based on the surfactant conservation. So that worked very well. So actually, right now, I'm not using this anymore. I moved to Erunge 4, but the idea is exactly the same. And what I want to say about it is that so the implicit term, so the diffusive term that we are treating implicitly, sometimes could cause problems in the sense that we need several iterations before converging, and depending on the drop shape, on the surfactant distribution, and so on. So in general, we need several iterations when the diffusivity was high, so when the Peclet number is small. So together with Anna Karin, we were able to build this preconditioner based on the fact that the spherical harmonics are eigenfunction of the Laplace-Beltrami operator on the sphere. So we have an explicit solution for the sphere. Of course, we are not dealing with sphere, but with spheroidal, like, with spherical topology. So this precondition turned out to work very well. As you can see from here, the number of iterations dropped drastically. So that was extremely important, especially in the simulation that I will show you today. So, okay, another thing that I didn't mention about my code is that I'm also using an adaptive upsampling introduced by Rahimian, always for vesicles. Why? Well, because it may happen that, so we have to compute several geometrical quantities, like, for example, the mean curvature of the drops. So it happens quite often that the drop shape itself needs very few spherical harmonics. Like, for example, if we consider an ellipsoid, it only needs one mode to be well represented by spherical harmonics. But if we look at the mean curvature, then the spectrum decays much slower. So we don't want to use a high P for the whole code. We would like to upsample only for computing the geometrical quantities that we need. And then we are using the same adaptive assembling introduced by Rahimian that is working very well also for drops. This means that, as I said, so my code is not adaptive in the general sense. I mean that P cannot change during the simulation, but it is adaptive in the sense that we can keep P small, and then the upsampling for the geometrical quantity will be adapted. We also have the special quadrant rule that I mentioned before, both for the singular and for the nearly singular integration. That means that, for example, in the simulation that I will show you later of drop pairs, we have two drops getting closer. They are not super distorted, so we can keep P quite small, but at the same time, in order to have a good quality of the integration, we need P high. So what we do is that we basically keep P very low for the whole simulation, and we set only the parameters of the nearly singular simulation. We push only those parameters so that we push only where we need to push. So in this sense, the code is adaptive. And also, well, of course, I also talk about the reparametrization and the adaptivity in time. Okay, so a few words about the asymptotic analysis. Okay, so before talking about what we did now for the drop pairs, let's start by the single drop. So the first thing that we did together with Petya is that, so if you have a single drop in an electric field, either a uniform or a quadrupole field, if the electric field is weak, is not too strong, the drop will deform, and then it also using the small deformation theory, first introduced by Taylor and then extended by others authors, as you can see here. So what we did with Petya is that we first extended this theory to second order for the quadrupole field, both in the clean case and in the surfactant-covered case. And this is for the single drop. And another approach is used to study the drop pair dynamics. So here again, there is some bibliography, but in all these studies, the author studied the droplet pairs aligned with the electric field. So they were in the same direction, while instead we are interested in a general configuration. So the drops can be anywhere. And we were able to get this solution for the velocity that holds in the case of a small deformation, so of weak electric fields. And it was super useful because we could study how this relative velocity depends on, of course, on physical parameters, which are in this case R, S, and lambda, where they are respectively the conductivity, the permittivity, and the viscosity ratios, and how this velocity depends on the distance between the drops and on the angle between the drops and the electric field. And so I wrote here only the solution for the clean case, but Patty extended this also for the surfactant-covered case. And we were able to basically make this phase diagram that guided us to discover new dynamics that I will show you now. So let's go to the validation. Okay, I will not list all the validation tests that I did, only the most interesting. So let's start by the single drop. So here I'm validating the code against experimental results and against the spheroidal model by Nganguya. So here is the drop is initially spherical with uniform surfactant concentration. Here are all the physical variables that, as you can see, are pretty, well, I mean, these are not super easy, like lambda 0, just to give you an idea, corresponds to a bubble. So this is not 0, but almost 0. And for this simulation, I used P equal 11, where P, I recall you, is the order of spherical harmonics. So as you can see, P is very small, and still we were in such a good agreement with both simulation and experiments. Okay, and then we validated also the drop in a linear field, in a quadruple field, against the second order extension. So in these plots, okay, so these two plots are for different parameters, and blue is for the surfactant-covered drop, black is for the clean drop, and the solid line is second order, and dashed lines is first order. So you can see that, yes, the second order is able to capture the dynamics much better in some cases. In other cases there is not this big difference. Anyway, this was the validation for the single drop. We also ran a convergence test to show the spectral accuracy of the code. So this is a section, but of course the drop was 3D. So we have an initially spherical drop again with uniform surfactant distribution. We switch the quadruple field on. So in this case, the drop will not only deform, but it will also translate, and then the surfactant will distribute on the drop. So we switch the electric field off at time 0.1, and then we look at the error. So here I'm plotting the error for both the position and the surfactant concentration. In blue, you can see the error that you obtain using the full method. Well, by full, I mean that I'm using the spectral reparametrization that I mentioned you before. And in black is the same simulation, but if I do not use any reparametrization. So even for such a short and easy simulation, you can see how important it is to have this spectral reparametrization that, yes, keeps the point distribution optimal for the whole simulation. And okay, another way of measuring the error is, of course, to look at the volume conservation. So again, you can see that we have spectral convergence, some like 10 to the minus 8 or so, because that was the tolerance in time that I set. Okay, so let's go to the drop pair now. So Baygents already started to study this problem both numerically and theoretically, but for an axisymmetric case. So he considered the drop aligned with the electric field in the Z direction. And he considered only clean drop, so without surfactant. And we do have the general configuration. But of course, we want to start by validating against Hirsch's result. So he was able to study how the velocity, the relative velocity between the drops should scale respect to the distance between the drops. And he could find that depending on physical parameters, the velocity should scale like d to the minus 2 or minus 4. And we could find very good agreement with his results, as you can see. And this is another study by Baygents in the same paper, where basically he showed the change of this slope depending. So we are plotting the relative velocity. I call it the steady velocity because basically what happens is that, so this is for uniform field. So the two drops initially deform, they become either oblate or prolate, and then they either attract or repel each other, and then they reach some steady velocity. And this is what we are plotting here. So versus the distance. So you can see that when the drops are close, the distance scales as -4, and then when they are getting far away, the slope changes. And we were in very good agreement, both our analytical solution and our numerical simulation. So after this, we move to more general cases where the drops are not aligned with the field anymore. And we started by comparing the droplet trajectory, the theory and the simulation. So, okay, so at the beginning, we have the drop were placed at an angle 50 and then distance 3.5. So as you can see from here, the distance is decreasing, which means that the droplets are attracting each other. And at some points, they change, the radial velocity change sign is, so it was negative at the beginning, then it becomes positive, and then the drops start to repel each other. And so in black is our simulation, and in red is the theory. And you can see that there was really good agreement for all these quantities, the separation, the radial velocity, the tangential velocity, and also the angle between the electric field and the drops. And then, okay, so as I said at the beginning, there are not so many references that we can, I mean, this is a pretty unexplored field, so we didn't really know what to expect. And guided by the theory, so at the beginning, we expected to see only attraction or repulsion between the drops. But guided by the phase diagram that I showed you before, we were able to set the physical parameter in such a way that we could find also this more interesting dynamics. So here are two cases for oblate deformation. So in this case, you can see that, well, at the beginning, of course, the drops deform, and then they start to attract, but then they reach some critical distance, and then they start to repel. And here is another example where we always have the oblate deformation, but the two drops keep on, so at the beginning, they repel each other for a very short time, and then they start to attract, and then they align with the field. And then we were able to find a similar behavior also for the prolate shapes. So in this case, the two drop become prolates and then start to attract and they repel, or the other way around. So all new dynamics. That was very fun to find. But then we, as I said, we also have extended this study for surfactant-covered drops. So in general, we could see that the qualitative behavior of surfactant-covered drops is quite similar to the clean drops. But again, guided by the theory, we were able to set the parameters in such a way that we could see how the surfactant can actually affect the simulation. So in this case, you can see all the physical parameters are the same. It's just that here I do have surfactant and here are for the clean drops. So with surfactant, well, first of all, we can see that the time scale are very different. So the two drops attract each other and they align with the field, while instead for the clean case, they start to attract, but then they reach the critical angle and then they repel each other and they misalign with the field, as it's clear from this plot where the arrows are the velocities of the two drops. Okay, so a few words about the future. So as I said, I do have this nearly singular quadrature, but I do not have error estimates. So I cannot set all the parameters automatically. And this is something that would be great to have. So together with Anna-Karin Thunberg and Ludwig af Klinteberg, we are working on error estimates for these 3D integrals. And once we finish this part, I would like to work on the interpolation problem to set all the parameters that I mentioned before. We are on the good way. As you can see, here is some results for a 3D surface. So here I'm plotting the numerical error in colors, and then the black lines are the estimates. So you can see that they follow pretty well the actual error. And then I would also like to release at the beginning, when I introduced the electric field equations, I told you that I'm neglecting all the unsteady terms for the charge density. So I would like to consider instead also these terms and the charge convection. because this can lead to more dynamics, like for example, the Quincke regime. So the drop will start tilting and rotating. So we are working on this now. I would also like to consider confined and periodic geometries and to couple my method with some fast methods. And now that I'm back in Rome, I'm also collaborating with Professor Lancia on boundary integral methods for fractal geometry. So everything that I presented now was for smooth geometries, but what happens if I do have fractal geometries? That's it, and there is some reference if you're interested, and that's it. Thank you.
Great, thank you very much, Chiara.
Thank you.
For a very interesting talk. So I'm sure there's going to be a lot of questions. So let me open it to questions.
Sure.
You either put them in the chat or just unmute your mic and ask a question.
Okay, I don't know if I can see the chat, but okay.
I have a question.
Andrew, yes, please go ahead.
I've got two questions actually, but I'll start with the physical one first. Do you have an explanation for what's going on with this attraction and repulsion that you were seeing as to why?
Yes, so I
happening?
think that, okay, like those examples here, yes. So Petya is probably the best person to answer your question, but the idea is that basically there is an interplay between the electrohydrodynamic flow and the electrophoresis induced by the dipoles. So so depending on like how big is each contribution, you may switch from one dynamic to the other. But I don't know if Petya wants to add something.
Well, that's the general idea. There is these two contributions, so that, and also when the droplets, you know, the line of centers, when it rotates, they can cross over from, like they can move from region of attraction to region of repulsion. And so it's quite complicated. That's why we built this phase diagram. So if you can pull the phase diagram, Chiara, there is a special discriminating function which tells us which way the line of centers is gonna rotate. So the shaded region is where the droplets actually rotate away from the field direction. And then, as I said, you know, when they rotate, also the balance between attraction and repulsion changes. So there is the if you look at the radial velocity, which is has the you know, there is the stress-led contribution, which is you know, with the beta T term, which is the depends on this is the electrohydrodynamic flow, and then you have the dipole, which has a different distance. So also as the distance changes, the relative importance of the two interactions changes. So yeah, so it's quite
so
complicated.
many contributions, yes.
Yeah, sorry.
But
for
if you then
too
change
long.
your external flow to force, could you drive it differently?
Yeah.
So right now the flow is due to the electric field,
exactly.
Right?
So if we put it in an external flow,
then the dynamics is going to get completely different.
Yeah, so in the general formulation I wrote yes, at the beginning I wrote a general far field velocity, but in those simulations like U infinity is 0, so but of course you can play as you want.
Yeah, I mean, I'm thinking particularly if it's to do with the rotation, if we put in a bit of swirling flow there.
It's exciting to check it out. So we haven't looked at the combined effect of external electric field and applied flow. So how this is gonna stir things around, it's another big question.
Yeah, that's interesting. Thank you.
And did you get any solutions where the two droplets came very close together to really test?
Well, yes, like in general, as I said, well, if we do not set any special value, the drops will either attract or repel each other. But also in where is it? There is some movie. But okay, so for example, or in here, I don't know why this doesn't go. Okay, you can see that they are getting closer. Then at some point, if the attraction keeps on acting, the drops would just the there would be coalescence. So my code does not allow for this change of topology. So I just have to stop the simulation at some point.
But there's no kind of surfactant distribution that will prevent that kind of Marangoni kind of.
Yeah, well, actually, we have seen that, yes, I didn't put several movies here, but we have seen that in some cases, yes, the surfactant will stop the flow. So yes, the answer is yes. Even if they are attracting, the surfactant will act, and then it will actually, yes, stop the flow.
Well, that's very important, right, for stabilizing foams and things. And yes. in these computations, the viscosities were equal in and out?
Yes, so in all these, so for the one drop cases here, I explored several ranges. For these new studies with drop pairs restricted with lambda equal 1, because I mean, there were so many variables already to explore, and also like it was more interesting to look at these other cases. And but theoretically, where is it? If you look, no, sorry, the phase diagram. So the theory is for general lambda. So it just changes the area of this shaded area, as you can see.
Yeah, good. Questions?
I should add that the code is not restricted for viscosity ratio 1. It's just it is something on the to-do list for Chiara to explore next. Is how the dynamics depends on the viscosity contrast.
Yes, but also like for one drop there are general viscosity. This was a very small viscosity, for example. So yeah. And actually, like actually, I also showed like the comparison with Baygents here. It was for lambda different than 1, right? Was it? Or I don't know. But we tested for several lambda, so it works. It's just that we didn't explore it numerically.
Okay. Yeah. Any questions?
I was just wondering, Chiara, given that your code includes surfactants, which is already a nonlinear effect, how does that, is that more complicated or same level of complexity as adding advection of surface charge?
Well, that's a good question, but adding the surface charges looks at, I mean, we are at the beginning, so I cannot answer for sure, but it looks much more complicated because the surfactant distribution always looks somehow smoother than the charge distribution. So what we are seeing now is that the charge distribution, the charge convection may bring shocks.
Yeah.
Which is tricky.
Can you comment, perhaps I guess you don't know yet, but maybe you have some intuition for what happens to those charge shocks when you have a pair of drops?
No, we are still looking only at a single drop because we are trying to see the Quincke regime. So we are kind of perturbing our charge distribution in order to see this rotation. But we are looking only at one drop for the moment. So I don't know for drop pairs yet.
And actually, for a single drop, do we know what happens to the charge shock if you add in surfactants?
I hope that it will help, but no, I don't know yet. So right now I'm looking at a single clean drop, and we are trying to understand if this Quincke regime will help or not with the shock, because when the drop will start to rotate, the charge will redistribute in a smoother way. Mm-hmm. So we hope that this will help, but I'm still exploring. So.
Okay, thank you.
But a good question, thank you.
Yeah, I've got about kind of a modeling question, I guess. With with all these surfactants, if you switch on electric fields, do they get electrified as well? I mean, can they also respond?
The surfactant,
they get charged?
I don't know.
That's a good question. That's a physics question. Yes, you can have actually charged surfactants. And then in the surfactant conservation equation, then you have to add also the electromigration. So it's, yet another level of complexity in the model that, yes, it's very interesting to see how like you can have a flow which is pushing the surfactant in one direction, but the surface flow, but then you can have the electromigration, which is trying to put the surfactant, let's say, in the opposite direction. So who knows what we're going to see.
Mm-hmm. Yeah, very, very complex.
Yeah.
Yeah, very rich, and I'm grateful that Chiara was able to develop the code so we can finally explore all these dynamics.
I have another question, if I may.
Yeah, please.
Yeah, a more technical question about your reparametrization.
Mm-hmm.
So, if I understood correctly, you're reparametrizing, but you're not remeshing per se. So you're redistributing the existing nodes, is that right? You're not allowing for changes in numbers or connectivity.
Exactly. Yes, you said it correctly. Yes. So I'm just saying, yes, reparametrizing. So the number of points are the same, and I'm just representing the same surfaces with the points in a different position.
And how exactly do you ensure that they stay on the same surface once it's deformed? Was that constraint?
Yes. So no, that's a good question actually. So okay, so well, in my let's say spectral reparametrization, this is embedded because okay, so let's go to the representation of my quantities here. So this is how my surface is represented. Okay, so by this okay. So as I said before, I'm reparametrizing. That means that instead I have this optimal velocity that I use to move the points in the optimal way. But I don't really do that. I built a new system, and I solve, instead of solving for the optimal velocity, I solve for the optimal theta and phi.
Okay.
So let's say that I can find the optimal theta and phi, I just use this. So,
okay,
and the coefficient, okay.
And then it's always on. So then that leads to my next question, which is how far do you think you can push this representation to non-spherical drops?
Okay, so if I have edges or so, of course not. But so in those examples that I showed you at the beginning, like here, I mean, there, non-spherical. Of course, if I have strong deformation like this, I need to push P much more. So in general, I do have like spherical shapes, and then I can keep P very small and push only where needed, as I said before. But for this kind of simulation, when the electric field is very strong, I need to push P for the whole simulation. But I mean, in all the simulation that I showed you, P was really small, like 9, 11, 13 at the most. And those are like 19 or so, so still very small. So I didn't try to push it more, but yeah, that's my general answer.
Okay, yeah, thank you.
Thank you.
Okay, thank you. Any other questions? No. Oh, if not, then please join me in thanking Chiara again for a really interesting talk. Some very exciting results. So looking forward to seeing more.
Yes,
so I'll stop the recording, and if people want to stay around and discuss more, you're welcome to. So thanks again, Chiara.
Thank you.